name is Ahmed, and in this video I'm going to talk about the TCA cycle, which is also known as the Krebs cycle, or the citric acid cycle. The primary substrate used in the TCA cycle is acetyl-CoA, which can be derived from pyruvate. While amino acids can also be used as substrates for the cycle, and acetyl-CoA can be obtained from beta oxidation of fatty acids, I'm only going to focus on acetyl-CoA derived from pyruvate. Glycolysis is a pathway in which glucose is broken down into pyruvate. Pyruvate is then converted through a series of reactions into acetyl-CoA. This process uses three enzymes that are bound together in a very large complex called the pyruvate dehydrogenase complex. The complex consists of several molecules that are bound together. If the molecules are enzymes, then the complex usually acts as one large enzyme catalyzing a big reaction or several sequential reactions. The dehydrogenase produces molecules like NADH and FADH2, which are electron carriers used in oxidative phosphorylation. The electron carrier produced by pyruvate dehydrogenase is NADH. To simplify the pictures used in this animation, I will draw all the molecules by the number of carbons that they contain. Acetyl-CoA, which is made up of 2 carbons, will be shown as 2 carbon balls. Notice that here the carbon balls are not connected, whereas in reality they would be connected by carbon-carbon bonds. The pyruvate, from which acetyl-CoA is derived, consists of 3 carbons. This is because during the pyruvate dehydrogenase reaction, one of pyruvate's carbons is lost as carbon dioxide, or CO2. The citric acid cycle begins when oxaloacetate, which is a 4-carbon molecule, combines with the 2-carbon molecule acetyl-CoA to form a 6-carbon molecule called citrate. Citrate is where one of the names of the citric acid cycle is derived from. Citrate then gets converted to cis-aconitate, which is then converted to isocitrate. All 3 of these molecules are 6-carbon compounds. Isocitrate then becomes oxidized into alpha-ketoglutarate. When isocitrate is oxidized, a carbon dioxide is released and another NADH is produced. Alpha-ketoglutarate is therefore a 5-carbon compound. A similar process occurs again, in which another carbon dioxide is released and a second NADH is produced. The 4-carbon compound left is then called succinyl-CoA. Succinyl-CoA is then converted into succinate, producing a GTP in the process. GTP is equivalent to ATP, as they are both nucleotide triphosphates. Succinate is then converted into fumarate, which makes the first and only FADH2 in the cycle. Fumarate gets then turned into malate, which is then oxidized to oxaloacetate, one of our initial starting materials. The oxygenation of malate produces the 3rd and final NADH molecule. Here's an overview of all the enzymes involved. Citrate synthase combines oxaloacetate and acetyl-CoA to form citrate. Aconitase then turns citrate to cis-aconitate, and then into isocitrate. Isocitrate dehydrogenase then turns isocitrate into alpha-ketoglutarate. This produces an NADH and a carbon dioxide. Alpha-ketoglutarate dehydrogenase then turns alpha-ketoglutarate into succinyl-CoA. This produces another NADH and another CO2. Succinyl-CoA synthase then turns succinyl-CoA into succinate. This produces GTP. Succinate dehydrogenase makes fumarate from succinate, releasing the only FADH2 in the cycle. Fumarate then gets turned into malate using fumarase. In the last step, malate is reoxidized to yield oxaloacetate, which can be used in another cycle. The oxidation produces the 3rd and final